The NX bit, which stands for no execute, is a technology used in CPUs to segregate areas of memory for use by either storage of processor instructions or for storage of data, a feature normally only found in Harvard architecture processors. However, the NX bit is being increasingly used in conventional von Neumann architecture processors, for security reasons. An operating system with support for the NX bit may mark certain areas of memory as non-executable. The processor will then refuse to execute any code residing in these areas of memory. The general technique, known as executable space protection, is used to prevent certain types of malicious software from taking over computers by inserting their code into another program's data storage area and running their own code from within this section. One class of such attacks is known as the buffer overflow attack. Intel markets the feature as the XD bit, for execute disable. AMD uses the marketing term enhanced virus protection. The ARM architecture refers to the feature as XN for execute never. It was introduced in ARM v6. Hardware background: x86 processors, since the 80286, included a similar capability implemented at the segment level. However, current operating systems implementing the flat memory model cannot use this capability. There was no executable flag in the page table entry in the 80386 and later x86 processors, until, to make this capability available to operating systems using the flat memory model, AMD added a no-execute, or NX bit to the page table entry in its 64 Armenian DRAMs architecture, providing a mechanism that can control execution per page rather than per whole segment. The page-level mechanism has been supported for years in various other processor architectures such as DEC Alpha, Sun SPARC, and IBM System/370XA, System/390, Z architecture and PowerPC. Intel implemented a similar feature in its Itanium processor having IA64 architecture in 2001, but did not bring it to the more popular x86 processor families. In the x86 architecture it was first implemented by AMD, as the NX bit, for use by its 64 Armenian DRAMs line of processors, such as the Athlon 64 and Opteron. The term NX bit itself is sometimes used to describe similar technologies in other processors. After AMD's decision to include this functionality in its 64 Armenian DRAMs instruction set, Intel implemented the similar XD bit feature in x86 processors beginning with the Pentium 4 processors based on later iterations of the Prescott core. The NX bit specifically refers to bit number 63 of a 64-bit entry in the page table. If this bit is set to 0, then code can be executed from that page. If set to 1, code cannot be executed from that page, and anything residing there is assumed to be data. It is only available with the long mode and legacy physical address extension page table formats, but not x86's original 32-bit page table format because page table entries in that format lack the 63rd bit used to enable execution. Software emulation of feature: prior to the onset of this feature within the hardware, various operating systems attempted to emulate this feature through software, such as WX or XX Shield. They are described later in this article. An operating system with the ability to emulate or take advantage of an NX bit may prevent the stack and heap memory areas from being executable, and may prevent executable memory from being writable. This helps to prevent certain buffer overflow exploits from succeeding, particularly those that inject and execute code, such as the Sasser and Blaster worms. These attacks rely on some part of memory, usually the stack, to be both writable and executable. If it is not, the attack fails. OS implementations: many operating systems implement or have an available executable space protection policy. Here is a list of such systems in alphabetical order, each with technologies ordered from newest to oldest. For some technologies, there is a summary which gives the major features each technology supports. The summary is structured as below. Hardware-supported processors, emulation, or, other supported, or, standard distribution, or, release date, A technology supplying architecture-independent emulation will be functional on all processors which aren't hardware supported. The other supported line is for processors which allows some gray area method, where an explicit NX bit doesn't exist yet hardware allows one to be emulated in some way. Android equals, as of Android 2.3 and later, architectures which support it have non-executable pages by default, including non-executable stack and heap. FreeBSD equals, initial support for the NX bit, on x86-64 and x86 processors that support it, first appeared in FreeBSD current on June 8, 2004. It has been in FreeBSD releases since the 5.3 release. Linux equals, the Linux kernel currently supports the NX bit on x86-64 CPUs and on x86 processors that implement it, such as the current 64-bit CPUs of AMD, Intel, Transmeta and VIA. The support for this feature in the 64-bit mode on x86-64 CPUs was added in 2004 by Andy Klein, and later the same year, Ingo Molnar added support for it in 32-bit mode on 64-bit CPUs. These features have been in the stable Linux kernel since release 2.6.8 in August 2004. The availability of the NX bit on 32-bit x86 kernels, which may run on both 32-bit x86 CPUs and 64-bit x86 compatible CPUs, is significant because a 32-bit x86 kernel would not normally expect the NX bit that an x86-64 processor supplies. The NX enabler patch ensures that these kernels will attempt to use the NX bit if present. Some desktop Linux distributions such as Fedora Core 6 and OpenSUSE do not enable the HIGHMEM64 option by default, which is required to gain access to the NX bit in 32-bit mode, in their default kernel. This is because the PAE mode that is required to use the NX bit causes pre-Pentium Pro and Celeron M and Pentium M processors without NX support to fail to boot. Other processors that do not support PAE are AMD K6 and earlier, Transmeta Crusoe, VIA C3 and earlier, and Geode GX and LX. VMware Workstation versions older than 4.0, Parallels Workstation versions older than 4.0, and Microsoft Virtual PC and Virtual Server do not support PAE on the guest. Fedora Core 6 and Ubuntu 9.10 and later provide a kernel PAE package which supports PAE and NX. NX memory protection has always been available in Ubuntu for any systems that had the hardware to support it and ran the 64-bit kernel or the 32-bit server kernel. The 32-bit PAE desktop kernel in Ubuntu 9.10 and later, also provides the PAE mode needed for hardware with the NX CPU feature. For systems that lack NX hardware, the 32-bit kernels now provide an approximation of the NX CPU feature via software emulation that can help block many exploits an attacker might run from stack or heap memory. Non-execute functionality has also been present for other non-x86 processors supporting this functionality for many releases. ExecShield, Red Hat kernel developer Ingo Molnar released a Linux kernel patch named ExecShield to approximate and utilize NX functionality on 32-bit x86 CPUs. The ExecShield patch was released to the Linux kernel mailing list on May 2, 2003. It was rejected for merging with the base kernel because it involved some intrusive changes to core code in order to handle the complex parts of the emulation trick. Hardware-supported processors, all that Linux supports NX on, emulation, NX approximation using the code segment limit on IA32 and compatible, other supported, none, standard distribution, Fedora Core on Red Hat Enterprise Linux, release date, May 2, 2003. PAX. The PAX NX technology can emulate a NX bit or NX functionality, or use a hardware NX bit. PAX works on x86 CPUs that do not have the NX bit, such as 32-bit x86. While PAX provides a much more complete implementation of NX functionality than its closest competitor ExecShield, it is a far more invasive modification of the Linux kernel and may be more prone to break legacy applications. The PAX project started on October 1, 2000, targeting the Linux kernel 2.4 series, and was later ported to the 2.6 series. As of January 2012, the Linux kernel mainline does not ship with PAX, and the patch must be applied by hand. Hardware-supported processors, Alpha, 64 Armenian DRAMs, IA64, MIPS, PowerRISC, PowerPC, SPARC, Emulation, IA32, other supported, PowerPC, SPARC, Standard Distribution, Adamantix, Hardened Gentoo, Hardened Linux, Alpine Linux, release date, October 1, 2000. Microsoft Windows starting with Windows XP Service Pack 2 and Windows Server 2003 Service Pack 1, the NX features were implemented for the first time on the x86 architecture. Microsoft Windows uses NX protection on critical Windows services exclusively by default. Under Windows XP or Server 2003, a feature is called Data Execution Prevention, and it can be configured through the Advanced tab of System Properties. If the x86 processor supports this feature in hardware, then the NX features are turned on automatically in Windows XP Server 2003 by default. If the feature is not supported by the x86 processor, then no protection is given. Software DEP is unrelated to the NX bit, and is what Microsoft calls their enforcement of safe structured exception handling. Software DEP safe checks when an exception is thrown to make sure that the exception is registered in a function table for the application, and requires the program to be built with it. Early implementations of DEP provided no address space layout randomization, which allowed potential return to libc attacks that could have been feasibly used to disable DEP during an attack. The PAX documentation elaborates on why ASLR is necessary. A proof of concept was produced detailing a method by which DEP could be circumvented in the absence of ASLR. It may be possible to develop a successful attack if the address of prepared data such as corrupted images or MP3s can be known by the attacker. Microsoft added ASLR functionality in Windows Vista and Windows Server 2008 to address this avenue of attack. Outside of the x86 sphere, a version of NX also exists for Intel's IA64 which is implemented in Windows on that architecture. Hardware-supported processors, x86-64, IA64, F-Machine, Pentium M, AMD Sempron, Emulation, No, other supported, none, Standard Distribution, Windows XP Service Pack 2, Windows Server 2003 Service Pack 1, Windows XP Professional x64 Edition, Windows Vista, release date, August 6, 2004, in Windows 8 and above. The NX feature, together with PAE and SSE2, is a hardware requirement for installing the OS. NetBSD as of NetBSD 2.0 and later, architectures which support it have non-executable stack and heap. Those that have per-page granularity consist of Alpha, AMP64, HPPA, i386, PAC, SH5, SPARC, SPARC64. Those that can only support these with region granularity are i386, PowerPC. Other architectures do not benefit from non-executable stack or heap. NetBSD does not by default use any software emulation to offer these features on those architectures. OpenBSD WX. A technology in the OpenBSD operating system, known as WX, marks writable pages by default as non-executable on processors that support that. On 32-bit x86 processors, the code segment is set to include only part of the address space, to provide some level of executable space protection. WX makes use of the NX bit on Alpha, 64 Armenian DRAMs, HPPA, and SPARC processors. Intel 64 processors may or may not be supported, depending on hardware. 1. Intel added the NX support to its later chips. OpenBSD 3.3 shipped May 1, 2003, and was the first operating system to include WX. Hardware-supported processors, Alpha, 64 Armenian DRAMs, HPPA, SPARC, Emulation, IA32, Other Supported, None, Standard Distribution, Yes, Release Date, May 1, 2003. OS X OS X for Intel supports the NX bit on all CPUs supported by Apple. Mac OS X 10.4 only supported NX stack protection. In Mac OS X 10.5, all 64-bit executables have NX stack and heap. WX protection. This includes x86-64 and 64-bit PowerPC on the G5 Macs. Solaris has supported globally disabling stack execution on SPARC processors since Solaris 2.6. In Solaris 9, support for disabling stack execution on a per-executable basis was added. As of Solaris 10, use of the NX bit is automatically enabled by default on x86 processors that support this feature. Exceptions are made for the 32-bit legacy ABI's treatment of a program stack segment. The vast majority of programs will work without changes. However, if a program fails, the protection may be disabled via the Enforce Protect EEPROM option. Sun recommends that failures should be reported as program bugs. Functional comparison of technologies. Generally, NX bit emulation is available only on x86 CPUs. The sections within dealing with emulation are concerned only with x86 CPUs unless otherwise stated. While it has been proven that some NX bit emulation methods incur an extremely low overhead, it has also been proven that such methods can become inaccurate. On the other hand, other methods may incur an extremely high overhead and be absolutely accurate. No method has been discovered yet without a significant trade-off, whether in processing power, accuracy, or virtual memory space. Overhead Overhead is the amount of extra CPU processing power that is required for each technology to function. It is important because technologies that somehow emulate or supply an NX bit will usually impose a measurable overhead, while using a hardware-supplied NX bit will impose no measurable overhead. All technologies create overhead due to the extra programming logic that must be created to control the state of the NX bit for various areas of memory. However, evaluation is usually handled by the CPU itself when a hardware NX bit exists, and thus produces no overhead. On CPUs supplying a hardware NX bit, none of the listed technologies imposes any significant measurable overhead unless explicitly noted. ExecShield's legacy CPU support approximates NX emulation by tracking the upper code segment limit. This imposes only a few cycles of overhead during context switches, which is for all intents and purposes immeasurable. PAX supplies two methods of NX bit emulation, called segregate and page-leak. The segregate method imposes a measurable but low overhead, typically less than 1%. Which is a constant scalar incurred due to the virtual memory mirroring used for the separation between execution and data accesses. Segregate also has the effect of halving the task's virtual address space, allowing the task to access less memory than it normally could. This is not a problem until the task requires access to more than half the normal address space, which is rare. Segregate does not cause programs to use more system memory, it only restricts how much they can access. On 32-bit CPUs, this becomes 1.5 GB rather than 3 GB. PAX supplies a method similar to ExecShield's approximation in the page-leak as a speed-up. However, when higher memory is marked executable, this method loses its protections. In these cases, PAX falls back to the older, variable overhead method used by page-leaks to protect pages below the CS limit, which may become a quite high overhead operation in certain memory access patterns. When the page-leaks method is used on a CPU supplying a hardware NX bit, the hardware NX bit is used. No emulation is used, thus no significant overhead is incurred. Accuracy Some technologies approximately emulate an NX bit on CPUs that do not support them. Others strictly emulate an NX bit for these CPUs, but decrease performance or virtual memory space significantly. Here, These methods will be compared for accuracy. All technologies listed here are fully accurate in the presence of a hardware NX bit, unless otherwise stated. ExecShield: for legacy CPUs without an NX bit, ExecShield fails to protect pages below the code segment limit. Unprotect call to mark higher memory, such as the stack executable will mark all memory below that limit executable as well. Thus, in these situations, ExecShield schemes fails. This is the cost of ExecShield's low overhead. PAX, segregate does not rely on such volatile systems as that used in ExecShield, and thus does not encounter conditions in which fine-grained NX bit emulation cannot be enforced. It does, however, have the halving of virtual address space mentioned above. PageLeaks will fall back to the original PageLeaks method used before the speed-up when data pages exist below the upper code segment limit. In both cases, PAX emulation remains fully accurate. No pages will become executable unless the operating system explicitly makes them as such. It is also interesting to note that PAX supplies protect restrictions to prevent programs from marking memory in ways that produce memory useful for a potential exploit. This policy causes certain applications to cease to function, but it can be disabled for affected programs. Control over restrictions equals, some technologies allow executable programs to be marked so that the operating system knows to relax the restrictions imposed by the NX technology for that particular program. Various systems provide various controls. Such controls are described here. ExecShield supplies executable markings. ExecShield only checks for two ELF header markings, which dictate whether the stack or heap needs to be executable. These are called PTGNU stack and PTGNU heap respectively. ExecShield allows these controls to be set for both binary executables and for libraries. If an executable loads a library requiring a given restriction relaxed, the executable will inherit that marking and have that restriction relaxed. PAX supplies fine-grained control over protections. It allows individual control over the following functions of the technology for each binary executable: executable space protections, PageLeaks, segregate. Protect restrictions, trampoline emulation, randomized executable base, randomized map base. See the PAX article for more details about these restrictions. PAX completely ignores both PTGNU stack and PTGNU heap. There was a point in time when PAX had a configuration option to honor these settings. That option has henceforth been intentionally removed for security reasons, as it was deemed not useful. The same results of PTGNU stack can normally be attained by disabling protect restrictions, as the program will normally protect the stack on load. This may not always be true. For situations where this fails, simply disabling both PageLeaks and segregate will effectively remove all executable space restrictions, giving the task the same protections on its executable space as a non-PAX system. Windows: when NX is supported, it is enabled by default. Windows allows programs to control which pages disallow execution through its API as well as through the section headers in a PE file. In the API, runtime access to the NX bit is exposed through the Win32 API calls virtual alloc, X and virtual protect, X. In these functions, a page protection setting is specified by the programmer. Each page may be individually flagged as executable or non-executable. Despite the lack of previous x86 hardware support, both executable and non-executable page settings have been provided since the beginning. On pre-NX CPUs, the presence of the executable attribute has no effect. It was documented as if it did function, and, as a result, most programmers used it properly. In the PE file format, each section can specify its executability. The execution flag has existed since the beginning of the format. Standard linkers have always used this flag correctly, even long before the NX bit. Because of these things, Windows is able to enforce the NX bit on old programs. Assuming the programmer complied with best practices, applications should work correctly now that NX is actually enforced. Only in a few cases have there been problems. Microsoft's own .NET runtime had problems with the NX bit and was updated. XBOX. In Microsoft's XBOX, although the CPU does not have the NX bit, newer versions of the XDK set the code segment limit to the beginning of the kernel's data section. This was probably in response to the 007 Agent Under Fire saved game exploit. However, this change does not fix the problem, as the memory address from which the payload executes is well below the beginning of the kernel's data section. Starting with version 51XX, this change was also implemented into the kernel of new XBOX-ES. This broke the techniques old exploits used to become a TSR. New versions were quickly released supporting this new version because the fundamental exploit was unaffected. References. External links: AMD, Intel put antivirus tech into chips, Microsoft interviewed on trustworthy computing and NX, LKML-NX announcement, changes to functionality in Microsoft Windows XP Service Pack 2 Part 3, Memory Protection Technologies, Microsoft Security Developer Center, Windows XP SP2, Execution Protection.